Hello learners, and welcome to a video tutorial where we are going to talk about Gauss's law, and specifically I want to talk about the Q enclosed, the charge that's enclosed by our Gaussian surface whenever we are utilizing Gauss's law. So Gauss's law states that the total flux is going to be equal to the closed area integral of E dA, which is equal to, we've been saying, the Q enclosed over epsilon naught. Now this is all well and good as long as we have uniform charge distribution throughout our Gaussian surface. But what if we don't? What if we have something where the charge distribution is changing depending on where you are? Well, what I'm going to do is I'm going to say Q enclosed is actually the integral of dq, how that charge is changing with respect to time. Now, the integral dq can be different things depending upon what type of object you're talking about. So here I'm going to look at if I had, for instance, like a sphere or a cloud of charge where it was kind of distributed throughout in a non-regimented, non-even sort of way. So we would end up with this kind of volume charge density being a function of r, and that would be equal to, some function depending on, what type of distribution you have. So the integral of dq, how that charge is changing, that would be the integral of my volume charge distribution with respect to how volume is changing. Now, generally this rho r is going to be a function of where you are inside the sphere. So it will be a function of little r. Well, what I can do is I can replace dV, how my volume is changing. And what I'm going to do is I'm going to take a very small little shell like this, and I'm going to say it's out a distance little r, but it's got a thickness dr. Well, the volume of this shell would be the surface area of the shell, which would be 4 pi r squared, times the thickness, which would be dr. And you can replace dV with that right there. And that is going to be ever so useful when you are dealing with a problem that has a non-uniform charge distribution.